Today we're going to be looking at the potential difference in current, a section of 5.2. So this is the first big idea in 5.2, which is really a continuation from 5.1 in our IB Physics curriculum. And I want to discuss what is a potential difference and how in the world does it cause a current, and what do we really need to know about that, and what are the potential outcomes. So I have first, let's just go back to 5.1. I have a positive charge, and that positive charge is creating an electric field around it, and anything that enters that electric field, if it has a charge, is going to feel a force through, described by Coulomb's law. Whether it's a positive charge feeling a repelling force, a negative charge feeling an attractive force, if there is a charged object that enters into that electric field, it feels a force. And the farther you get away from that, the less that force will be. And that is defined as the electric field strength. But then when I start looking at the energy that would be given to those objects entering that field or required to move those objects around that field, we start talking about electric potential. And electric potential comes as a result of moving objects around in an electric field. So I have an object, and that's a very special object, very unique object. This is a battery, and a battery is a big thing of chemicals that we'll learn more about in 5.3, but there's going to be a very specific chemical reaction happening inside a battery that drives positive charge to one side and negative charge to the other. Really, it's a difference of electronegativity and my cathode and my anode, able to draw some ions through an electrolytic, but more on that later. So I have a positive charge on one side of my battery and a net negative charge on the other. And when those aren't connected to anything, if I get rid of this wire right here, you'll see that nothing happens. That positive and negative charges, they're not able to connect. They're separated by an insulator on the inside, and I'm left with not much going on. But the moment I hook these things up to a wire, a current carrying wire, a conductive wire that allows that positive and negative to interact, I can start to get a current to flow between those 2 points. So how in the world might that happen? And that's going to happen because I have a positive charge and a negative charge. And as a result of that, I'm going to get a net electric field going through my current carrying wire. It's going to be going from positive to negative. The specific mechanism of that is beyond the scope of the IB, but it deals with lots of surface charges building up, and wherever I connect that wire, I'm going to be getting some specific interactions happening. Leakage current or leakage voltage from my positive terminal, my negative terminal will cause that to be true, but that, like I said, that's beyond what we need to care about. So when I hook these up, I get a net electric field in that wire. So that electric field, because there is a constant charge on one side and a constant charge on the other side, it is uniform. So all points along this wire are going to have an equivalent electric field. And that allows all the objects inside that have a charge to want to move as a result. And so what is able to move inside my wire? Well, those are my little electrons. And so those little electrons are now interacting with this net electric field. They're still going to be drifting around, not following a specific path, bouncing around all over the place, but they're going to have a net movement towards, not towards the negative side, turn all those arrows around, towards the positive side, because the electrons are attracted to positive charges. And so what is causing that? That is caused by my potential difference. And so that is a very key thing. Without a potential difference, I get no current. So a electric potential difference causes a current. And so the potential difference, or the voltage, I'll put in parentheses, voltage causes my current, or it drives the current. If I make those charges bigger, so my net field is bigger, my current will increase. Because I have a greater potential difference. Yeah, so that should make sense. This field becomes stronger, my electrons move a little bit more in response to that change. And so my voltage, my potential difference, drives that current. And so the whole energy of this entire system comes from that potential difference, because we defined electric potential as the amount of energy required to move something through an electric field. That's what I'm looking at. So if I look at that potential difference, if I run this system in reverse, make those electrons go in the direction they don't want to go, how much energy would it require for me to move those backwards? That's the potential driving it forward. And so often you're going to see this idea through an analogy. And that analogy comes through some water description. So I have a water tower, which is, you can imagine that as gravitational potential energy. The water is free to move downhill, down slope, but something has pumped it up into this water tower. That something is going to be our electromotive force, which we'll learn more about later, but it's the mechanism of that reaction on the inside, is pumping that water up to an area of high potential. And then gravity is going to pull it down to a lower potential, until eventually it gets down to the bottom, down to the ground, and there's just a little puddle, and that little puddle of water can't do anything. It has no potential anymore. So that pump would pump that puddle back up in order to repeat that process again. And so to get water out of my water tower, I'm going to need to attach it some sort of pipe. And that some sort of pipe, the size of that pipe is going to determine my current. If I have a little barrier in that pipe, something that is resisting that flow of water, that's going to be equivalent to my resistance. But this water is going to want to naturally fall from high potential to low potential. Just like these electrons are naturally going to want to move from high potential to low potential, that current is taking them away until they get back to the other side where they have no more potential, ready to be boosted back up again. But the only thing that'll make that happen is if I put a device in here, some sort of resistor to take energy away. I'm not looking for a waterfall out of my water tower. I'm looking for a nice controlled steady flow, and that is only possible when I put a resistor in there, or else I have a short circuit and all that energy is released at once, and that's bad news bears, because all those electrons run into the nuclei and tons of heat is produced, and that's how you can burn a house down, or something that you don't really want to happen. And so I want you to look at this picture for a moment, and we'll spend a little bit of time talking about it. I currently teach in Egypt, and one of my students described this relationship to me because the word for mother in Egypt sounds very similar to the word And he said that he's got a lot of friends that often are some negative influences in his life, and they cause some peer pressure in trying to get him to do things. So he's this little current, this little electron moving around, trying to figure out what in the world is going on. And sometimes when he's around his friends, they get all excited and they try to encourage him, cause some peer pressure to do some things that his mom doesn't really want him to do. And so my voltage, as you can think about that as the peer pressure or the influences, the negative influences. Maybe that current wants to go there. Maybe it's some sort of addiction or drugs that he was talking about. But whatever is either pushing those electrons along or attracting those electrons, something is trying to get those electrons to do something. But then our resistance would be like a mother that's trying to slow things down, making sure things don't get too out of hand, because the mother really cares about her child and doesn't want anything bad to happen to them. So we need some resistance. We need some ohms in our life, some mothers to slow us down, to make sure we don't burn the house down. And so that's a little picture and hopefully a little mental memory that you can think about this um, in order to understand, to remember what ohms do, what amps are. Amps are the unit for current, volts, my potential difference, the driver making these electrons move at their whim, and then the mothers are trying to rein those in. So this is all about voltage for right now. And voltage, so break in my little story, voltage is the work done per unit charge, or I get joules per coulomb. And so if I take a device and I have a circuit and I measure the potential, the electric potential at a certain location. So I'm going to measure my electric potential here. And I see this is the 100-volt battery. I'm looking at the path of conventional current that's going around this way. So I've not ran into any device that wants to use any of that energy yet. So no work has been done. So my electric potential at this point is still 100 volts, or 100 joules per coulomb of charge at this location right here. Then there's some work that happens. It goes through a device number 1, resistor 1. I'm going to call that R1, R2, R3. And then I end up on the other side. And on the other side, I've made it through all of the pieces that are going to take energy away. And my electric potential over here is 0 joules per coulomb. I don't have any energy left to do more work. I still have current. I got to take that current still going back to the battery, but that current has been used up. All of that energy has been extracted by my resistors, and now it's heading back to my battery. So that's a key thing that we want to remember. Current is still flowing, and current doesn't change when I have this is a series circuit, when I have a series circuit. But the energy that those electrons have has been removed. The potential has been removed. So, started off with 100, ended with 0. Let's take our little voltmeter and measure at this point. And we see that at that point, there is 75 joules per coulomb, or 75 volts of potential. At that point, after I go through one resistor, I used some of that energy. I still have 75 joules per coulomb left. Still quite a bit, still can do some more work. Then I measure after my second resistor, and I see that there's 10 volts left, or 10 joules per coulomb. And then after my last resistor, I have 0. So when you start to think about these types of circuits and what is actually going on, when you start measuring potential difference, or measuring the voltage drop across the resistor, that is the change in potential from before to after that device. How much energy, how many joules per coulomb was extracted. And so if I look at R3, what is its potential difference? And you'll see that it started with 10, then it goes to 0. So it's delta V, its change in potential, its potential difference is 10 volts. What about R2? R2 went from 75 to 10. So R2 delta V is going to be 65 volts. That's a 65 volts. And then R1 is going to be 25 volts. So R1, the potential difference, is 25 volts, or 25 joules per coulomb. So for every coulomb of charge that went through there, 25 joules of energy was extracted. And so that is the idea of potential difference and driving a current. And then that energy is being used up, but the current is not. So whatever the current would happen to be inside the system, if I took my other device, my ammeter, let me get out a different color for ammeter, see if we can find something unique and different. Maybe this nice purple over here. If I put my ammeters are supposed to be in series, one before anything happens and one after everything happens. If that ammeter reads that there is 2.5 amps of current, then at the end, there have to be 2.5 amps of current. I'm not getting rid of electrons in this. I'm only getting rid of the energy those electrons have. So the current didn't change, just the energy that those electrons were carrying did change. All right, so potential difference. I need that potential to cause a voltage, to cause a current, and then I need some resistance to make sure that that current stays constant or doesn't overheat anything. All right, so here I have 3 different circuits. And in these circuits, I have a light bulb A, B, C, D, E. And I want to just do a little bit of ranking of what in the world, which one of these bulbs is going to be the brightest. I've got a 10-volt battery in each one of these circuits. And then in circuit 1, all I have is just a battery. Just a single light bulb. In circuit 2, I have 2 light bulbs in parallel. In circuit 3, I have 2 light bulbs in series. And so if we want to think about, we should be thinking that voltage is energy available per coulomb. I need to see how much energy is available for each one of my light bulbs. What is that potential before and after, that potential before and after, before and after, before, after, before, and after. And the more energy that is used, the brighter my light will be, if they have the same resistance and if the bulbs are equivalent. And if they're not, then we have a whole different problem to deal with. But for this scenario, all of our light bulbs are the same. So which one's going to be the brightest? I can see that A is connected on one side to a plus 10 and on the other side down to 0. So my delta V, it lost 10 volts or 10 joules per coulomb. That's pretty bright. I go down, and that's the only thing in that circuit, so that bulb A is using 10 volts. That's as bright as it can be because that's 10 volts is all I got. When I look at B, and I look and I see, what is that connected to? What's that positive terminal? Well, there's nothing in front of B. So coming in, it's 10 volts, or 10 joules per coulomb, and leaving, what's that other side connected to? Well, it's not running into anything else, so it's going to go down to 0 volts. It's made it to the puddle on the bottom. So my delta V for B is also 10 volts. C, I can take a path right back to the battery from top to bottom, so that delta V is also 10 joules per coulomb. I'm mixing up my units intentionally just so you can get that in your mind, that voltage is energy per coulomb, so I can think about it as energy, or I can think about it as potential difference. But now I get to circuit number 3. In circuit number 3, I start off, that battery, one side of that battery, it's connected to 10 volts. The other side of the light bulb, it runs into a light bulb over there. And I have to go to the other side of E to get to 0 volts. So if these 2 light bulbs are identical, that means that half of the energy is going to be used in D, and the other half is going to be used at V. So if I measure the potential here, there should be 5 volts. 5 volts of energy, half that energy was used in D, so my delta V is 5 joules per coulomb. And for E, my delta V is also 5 joules per coulomb. So to figure out which one of these lights is the brightest, it has to have the most potential difference. And I can see that A equals B equals C because they all have PD, potential difference, of 10 joules per coulomb. So they all are using that much energy. And those are all greater than D and E, because those are each using 5 joules per coulomb. Because they're in series, they have to share that potential difference. And so by looking at potential difference, I can look at how much energy they're using, and then that lets me have a little intuition and insight into how bright those bulbs will be. All right, so in summary, voltage drives potential. Drives current. When I want to think about resistance, resistance uses energy or reduces potential. So taking that energy out, taking that energy out by my resistor is converting that energy to something else. If I don't have a resistor, I have a straight wire from here to here. Straight wires have no PD, or essentially no potential difference. We'll learn that that isn't necessarily true. There is some resistance in wires, but it's very small and almost negligible. So that's something that I need to remember. When I go all the way around a circuit, so potential, when I go all the way around a circuit, all energy is lost, is used up, used by the devices or resistors / resistors. All right, so that's my summary. My voltage drives the current, resistance uses energy and reduces the potential. If there's no potential, if I have straight wire, there's no potential difference in that wire and no energy is going to be used. When I go all the way around a circuit, all the energy that is available is now going to be used up by those devices, and I get back to zero potential, back to the puddle at the bottom, as you saw in that original picture. And so thank goodness for your mother, that ohm that's going to keep you in check and keep you in line. We need those ohms to keep our houses from burning down. All right, I hope this was helpful and gave you a little understanding into what electric potential is and how that causes a current. Thank you. Have a good day.